Now I'll be starting with chemistry unit 6 of class 12, that is the organic chemistry, haloalkanes and haloarenes. Halogenated compounds persist in the environment due to their resistance to break down by the solid bacteria. Let's come back to that, but let's see the objectives here. The objectives or the topics in this lessons, mainly the topics description. After studying this unit, we will be able to name haloalkanes and haloarenes according to the IUPAC system of nomenclature from their given structures, describe the reactions involved in the preparation of haloalkanes and haloarenes, and understand various reactions that they undergo, correlate the structures of haloalkanes and haloarenes with various types of reactions, use stereochemistry as a tool for understanding the reaction mechanism, appreciate the applications of organometallic compounds, highlight the environment effects of polyhalogen compounds. Just a minute. Okay. Now let's start with the chapter. Halogenated compounds persist in the environment due to their resistance to break down by solid bacteria. Normally, complex compounds are broken down by bacteria that is present in the soil into simpler compounds, but halogenated compounds, they do not get decomposed by bacteria because of their resistance to break down by these bacteria. Okay, that is the first line here. The replacement of hydrogen atoms in an aliphatic or aromatic hydrocarbon by halogen atoms results in the formation of an alkyl halide or a haloalkane and an aryl halide or a haloarene, respectively. Basically, when we replace hydrogen atoms in an aliphatic or aromatic hydrocarbon by halogen atoms, result in the formation of haloalkane and haloarenes. In from a hydrocarbon, we remove a hydrogen. In that place, we substitute chlorine, is called as a haloalkane. In case of an aliphatic, which means it is not an aromatic compound, and aromatic compounds, it is haloarene. Haloalkenes contain halogen atoms attached to the sp3 hybridized atoms and of an alkyl group, whereas haloarenes contain halogen atoms attached to sp2 hybridized carbon atom of an aryl group. Many halogen containing organic compounds occur in nature, and some of these are clinically useful. Okay, basically there are a total of three information given here in these the lines I read. The first information is when hydrogen is replaced in a hydrocarbon, if hydrogen is replaced by a halogen, then it's called a haloalkane or a haloarene. In case of haloalkenes, the the normally in general case, the haloalkenes, the hydrogen will be the halogen will be attached to an sp3 carbon, but in case of haloarenes, generally the halogen will be attached to an sp2 hybridized carbon. Many halogen containing organic compounds occur in nature. The third information here is many halogen containing organic compounds occur in nature, that is because they persist in the environment due to their resistance to break down by soil bacteria, and some of them are clinically useful. These classes of compounds find wide application in industry as well as day-to-day life. They are used as solvents for relatively non-polar compounds and as starting materials for the synthesis of wide range of organic compounds. They are saying uses here, the first use is they are used as solvents for relatively non-polar compounds, as non-polar like dissolves like, polar is dissolved in polar, non-polar is dissolved in non-polar. So for non-polar compounds, as these organic compounds are also mostly non-polar, in such a case we use these compounds as solvents, and in other case is for creating various other kinds of organic compounds, that may be fertilizers or anything like that. These compounds of alkyl halides are used for as a starting product, like starting reactant. And containing antibiotic chloramphenicol produced by microorganisms is very effective for the treatment of typhoid fever. Basically, chloramphenicol produced by microorganisms. It is a chlorine containing antibiotic. It is very effective against treatment of typhoid fever. This is what they mean by clinical usage. Basically, for medicine, it works as a medicine. When there is body like typhoid fever, our body produces iodine containing hormone, that is thyroxine, a deficiency in which causes a disease called goiter, and synthetic halogen compounds. Chloroquine is used for treatment of malaria. Halothane is used as an anesthetic during surgery. Certain fully fluorinated compounds are being considered as potential blood substitutes in surgery. Basically, these are all applications here, what they can be used and what kind of compounds are used where here. The first is an antibiotic used effectively, which is very effective in case of typhoid fever, that is chloramphenicol. And about thyroxine, which is an iodine containing hormone, and the deficiency of thyroxine leads to goiter. And there is also chloroquine, which is used in treatment of malaria. Let me highlight it again in different color. Chloramphenicol, treatment of fever produced by microorganisms. Iodine, thyroxine, deficiency, disease called goiter, synthetic halogen compounds, chloroquine used for treatment of malaria, halothane, anesthetic during surgery. Fully fluorinated compounds are considered as potential blood substitutes. Okay, in this unit, you will study the important methods of preparation, physical and chemical properties, and uses of organohalogen compounds. Now, the first topic is classification. Haloalkanes and haloarenes may be classified as follows. That is, on the basis of number of halogen atoms. They may be classified as mono, di, or polyhalogen, tri, tetra, etc. compounds, depending on whether they contain one, two, or more halogen atoms in their structures. For example, this in case of this compound, there is only one halogen compound, one X. X denotes the halogen compounds. X is for halogen for 17th group elements. Here it is monohaloalkane because only one halogen atom. Here dihaloalkane because two halogen atoms. Here trihaloalkane, three halogen atoms. And here in case of arenes, because they are aromatic compounds, we call it as arenes. Here it is monohaloarene, dihaloarene, and trihaloarene. Very simple actually. Monohalo compounds may further be classified according to the hybridization of the carbon atom which the halogen is bonded to, that is discussed below. Basically, the first kind of classification is based on the number of halogen atoms, that is done. The next is based on In this case, if we see here, in the first compound case, the halogen is attached to, this is the structure. In this case, this carbon is sp3 hybridized. Here, this halogen is attached to an sp3 hybridized carbon. And let's take another case. In the second case, it is in case of benzene. If we take here, in this case, this carbon is sp2 hybridized because of this double bond here. It's a pi bond, so it is sp2 hybridized. In this case, the carbon is sp2 hybridized, not the halogen, but the halogen is connected to an sp2 hybridized carbon. That is what they're talking about. Based on this, we classify the second kind of classification. The first classification is based on number of halogen atoms. The second kind is based on what is the hybridization of the carbon the halogen is connected to. Compounds containing sp3 CX bonds, and this class includes, this may be X double bond F, Cl, wait, that's not X double bond. This X can be fluorine, chlorine, bromine and iodine. Basically, that's an equal to sign. A, alkyl halides or haloalkenes, which is the RX bond. In alkyl halides, the halogen atom is bonded to an alkyl group. They form a homologous series represented by CnH2n plus 1x. They are further classified as primary, secondary, tertiary according to the nature of the carbon which halogen is attached to. If halogen is attached to a primary carbon in an alkyl halide, the alkyl halide is called as primary alkyl halide or primary alkyl, like this they are representing a simple. Similarly, if halogen is attached to secondary or tertiary carbon, the alkyl halide is called as secondary alkyl halide and tertiary alkyl halide respectively. The information they gave here is the general information. The information they gave is the homologous series represented by, form a homologous series represented by CnH2n plus 1x. They are further classified into primary, secondary, tertiary according to the nature of the carbon which is attached to it. Okay, the main important points are highlighted like that, but it is better to further classified as primary, secondary or tertiary according to the nature of the carbon which halogen is attached. Now this is the primary, where it's the carbon is only attached to one carbon. Secondary, where the carbon is attached to two carbons. Tertiary, when the carbon is attached to three carbons. The halogen attached to a carbon attached to three carbons is the tertiary. The halogen attached to a carbon attached to two carbons is called as secondary, and the halogen attached to a carbon attached to a single carbon is called as a primary halide. Now let's go to allylic halides. These are the compounds in which the halogen atom is bonded to an sp3 hybridized atom adjacent to an carbon-carbon double bond, that is an allylic carbon. Basically, when the halogen is attached to a carbon that is attached to a sp2 hybridized carbon, then we call it as allylic halogen or allylic compound or allylic carbon, where the carbon which is attached, this carbon is sp2, but this carbon here is not sp2. Now let's go to the next main topic, that is benzylic. These are compounds in which the halogen atom is bonded to an sp3 hybridized carbon atom attached to an aromatic ring. Okay, these are hybridized These are the compounds in which halogen atom is bonded to an sp3 hybridized carbon atom, which is attached to an aromatic ring, same like allylic, but in this case the sp2 bonding is provided by, like, sp2 carbon is a part of the allylic ring, not allylic, benzylic ring, where it's a part of the aromatic compound, where this carbon and this carbon are sp3, but this sp3 carbon is attached to an sp2 carbon, like here. So this is the benzylic arrangement similar to allylic, but allylic there is no benzene ring. In benzylic there is a benzene ring, easily to be understood through the naming sense itself. Compounds containing sp2cx bond. This class includes vinylic halides. These are compounds in which the halogen atom is bonded to an sp2 hybridized carbon atom of a carbon-carbon double bond, C double bond C. And in before cases, in allylic and benzylic cases, we saw that the halogen was attached to a carbon which is sp3 hybridized, which is attached to an sp2 hybridized carbon. But here in the vinylic and arylic cases, the halogen is directly attached to an sp2 hybridized carbon. An sp2 hybridized carbon, it is directly attached to a sp2 hybridized carbon, like this. This is not a benzene, this is a cyclohexene. And in case of aryl halides, these are compounds in which halogen atom is directly bonded to an sp2 hybridized carbon atom on an aromatic ring. If the halogen is directly bonded to the aromatic ring, in the case of aryls and vinyls, it is bonded to an sp2 hybridized carbon. But why do we classify these in terms of attached to CH2 and, I mean not CH2, sp2 and sp3 hybridized or orbitals, like not orbitals but hybridization? I'm not too sure. Why do we need to classify haloalkanes and haloarenes? That's a short name, but I spelled it wrong. Alkanes and haloarenes in terms if the halogen is connected to a sp3 or sp2 carbon, and even more so if that carbon is connected to sp3 or sp2 carbons. Why does this matter? Further on, the hybridization of neighboring carbon atoms is not just a formality, it has been chemical and physical implication, especially reactivity and reaction mechanism. The hybridization of the carbon bonded to halogen directly affects the type of reaction it can undergo, especially nucleophile substitution reaction and elimination reaction. In an sp3 carbon, the CX bond is polar and relatively easy to break, commonly undergo SN1, SN2, and E1 and E2 reactions. Electrophilic maybe. Reactivity is influenced by neighboring groups. sp3 carbon in haloalkanes and vinyl halides, the CX bond has partial double bond character due to resonance or pi back bonding, much stable and resistance to nucleophilic substitutions. Reactions may proceed only under drastic conditions or via alternative mechanisms. Bond strength and bond character. are shorter and stronger than sp3 bonds due to partial double bond character. The stronger makes it harder to break, so less reactive in substitutions. Basically, this seems to be related to reactions. That is what I thought, but just for confirmation. It is mostly dependent on the behavior and chemical reactivity. Fine, I guess. Now let's go to the next main topic, that is nomenclature. Having learned the classification of halogenated compounds, let us now learn how these are named. The common names of alkyl halides are derived by the alkyl group followed by the name of halide. In the IUPAC system of nomenclature, alkyl halides are named as halosubstituted hydrocarbons. For monohalosubstituted derivatives of benzene, common and IUPAC names are the same. For dihalogen derivatives, the prefixes ortho, meta, para are used in common system, but in IUPAC system, you have learnt in class 11 that numericals 1, 2, 1, 3, and 1, 4 are used. Basically, let's read that again. The common names of alkyl halides, they're talking about common names here. These common names of alkyl halides are derived by common names of alkyl halides derived by naming the alkyl group followed by the name of the halide. Okay, first we give the alkyl group name, like if we case in case of CH3Cl, we name it as, in case of common names, we name it as methyl chloride. And in case of IUPAC name, we name it, let's see the IUPAC nomenclature as well. Here they give it. In the IUPAC system of nomenclature, alkyl halides are named as halosubstituted hydrocarbons. In a common name, we call this as methyl chloride, but in case of IUPAC nomenclature, we call it as chloromethane or 1-chloromethane. That is what they said here. For monohalogen substituted derivatives of benzene, for monohalogen substituted derivatives of benzene, basically when in the benzene ring we have halogen substituents, like if there is only one halogen substituent, the name for IUPAC and common name is same for benzene when only a single halogen is substituted. But for dihalogen derivatives, that is when more than one halogen is substituted to the benzene ring, then common and then the IUPAC names, then the prefixes ortho, meta, and para are used in common naming system, common nomenclature system. But in the IUPAC system, we name it as 1, 2, 1, 3, and 1, 4 for ortho, meta, para positions respectively. These are some of the compounds where we see common name and IUPAC name is given. This is 1, 2, 3, 3 carbon, so it is 1 bromopropane according to the IUPAC nomenclature. But in case of common name, it is, since it's a straight chain, we call it as N. We gave it an N here. It's a straight chain, so it's an N. And we know that we name the halide first, not halide at the last, and alkyl at the first. So since there are 3 carbons, it is a propyl bromide. Since it's a straight chain, it is a N-propyl bromide. Now let's go to the second compound. Here it is 1, 2, 3 carbons as well, but we see the chlorine is substituted in a different position because it is like it's a isomer of this kind of compound. Let's assume if this chlorine substituted here, if such was the case, this would have been an isomer of this if there was chlorine instead of bromine here. So that is the reason they call it as isopropyl chloride. and in case of IUPAC name it is 2-chloropropane, and the third one it is 1 2 3 4, it is an isobutyl chloride. Since there are three carbons, it's a butyl, but since it is not a full chain butane, it is not a complete chain, and it's kind of an isomer, so it is called an isobutyl chloride, where the isomerism is seen in the main hydrocarbon chain instead of the chlorine chain or the halogen chain. And the IUPAC name is 1-chloro-2-methyl propane. The methyl is for the CH3 group. And for haloarenes, if we see, for a single halogen derivative, only one halogen is there in the benzene ring, then it is called bromobenzene in the common name as well as the IUPAC name. But in case of the when two halogens are substituted, it is called as meta dibromobenzene in case of common nomenclature, and 1 3 dibromobenzene in IUPAC nomenclature. And this one where there are three bromo derivatives, it is called as a symmetric tribromobenzene, and in IUPAC name it is 1 3 5 tribromobenzene. Here there is one more compound here, 1 2 3 4 5. Wait, 1 2 3 4 5, yes, 5 carbons. So it is in case of the IUPAC name it is 1-chloro 2 dimethyl propane. Here it is a true bromopropane. The dihaloalkanes having the same type of halogen atoms are named as alkidene or alkylene dihalides. Basically, when there are two halogen atoms in a hydrocarbon or an alkane which are of the same type, like in this case, wait, they did not show a case here, are named when there are two types of when there are two types of halides of the same element halides, like chlorine attached to a single haloalkane, attached to a alkane group, a single alkane compound, then we can name it as alkylidene or alkaline dihalides. The dihalo compounds have both the halogen atoms having both the halogen atoms are further classified as geminal or gem dihalides when both the halogen atoms are present in the same carbon atom of the chain, and vicinal halides or VIC halides when the halogen atoms are present on adjacent carbon atoms. Basically, this is this is the structure for geminal dihalides. This is the structure for vicinal dihalides. Vicinal meaning adjacent carbons, two different carbons have two different chlorine, but they should be adjacent to each other. But in case of geminal, both the chlorine atoms are attached to a single carbon atom. And common name, we saw that it was ethylidene chloride in case of a geminal dihalide, ethylidene chloride, or an ethylene dichloride in case of vicinal chlorides. In common name system, GEM dihalides are named as alkylidene halides, and VIC vicinal dihalides are named as alkaline dihalides. In IUPAC system, they are named as dihaloalkanes, where we name it as 1 dichloromethane in case of geminal dihalide and 1 dichloromethane in case of vicinal dihalides. Some common examples of halo compounds are mentioned in table 6.7. Let's see them. Common and IUPAC names of some halides. Structure. This is the structure where it is an SEC butyl chloride. IUPAC name is 2-chlorobutane is just it's just a butane group, but in the second butane carbon a chlorine is attached. It is a SEC. What is SEC in common nomenclature? Secondary. Okay, basically SEC means fine, leave it be, I guess. Secondary butyl chloride. And in case of this one, where this bracket indicates that there are three methyl groups attached to this single carbon, which we can identify because it is only attached to a carbon, and this carbon is attached only to a single carbon, and there is no hydrogen attached to it. So in this case it is a neopentyl bromide. Neo means having a tertiary group. 1 bromo 2 comma 2 dimethyl propane, that is the IUPAC name. CH3 thrice, this as well, tertiary bromide. Tertiary butyl bromide, 2 bromo 2 methyl propane. CH2 CHCl. Vinyl chloride, because it is attached directly there, directly to an sp2 carbon. It's chloroethane, and in this case it's an allyl bromide because it is attached to an sp3 carbon attached to an sp2 carbon. It is 3-bromopropene. This is an aromatic compound. Orthochloro Orthochlorotoluene is the common name. Toluene is thus benzene with CH3 group. Benzene with CH3 group is called as toluene, and here it is in the ortho position. So orthochlorotoluene, it is 1-chloro-2-methyl benzene in the IUPAC name, or 2-chlorotoluene. We can also call it as 2-chlorotoluene. In this case it is a benzyl chloride. Benzyl chloride. Okay, and it is chlorophenyl methane. There's also a chlorophenyl methane. You can call the IUPAC name is chlorophenyl methane. And in case of CH2Cl2, it is a methylene chloride or dichloromethane. This is the common name is CHCl3 is chloroform or trichloromethane, bromoform, tribromomethane, carbon tetrachloride, tetrachloromethane, and N-propyl fluoride or 1,1-fluoropropene. Draw the structures of all the 8 structural isomers that have the molecular structure C5H12H11Br. Name each isomer according to IUPAC system and classify them as primary, secondary, and tertiary bromide. The first case, the most simple case, is this one. In the second carbon here, secondary. In the third carbon here, tertiary. And in the first here, but it is still primary, but it is methyl butane, not a pentane. Here again same thing repeat. Again we take for a tertiary here, it will become a dimethyl propane. All of these are structural isomers. Write the names of the following compounds. This one, 1 2 3 4 and 5. So 1 2 3 4 5 carbons in the main chain. So it is 2 bromo 4 methyl pentane. It is 4 bromo Okay, 4 bromo pen 2 in. Okay, this is not outside the chain. I'm sorry about that. Okay, and the second one is 1 2 3 4. This is most likely in the outside the main chain, and so it will be 2 methyl and 3 bromo 1 2 3 4 butane, 2 methyl 3 bromo but 1 in. Yes, that is correct. Here it is 1 2 3 4, basically all similar structures, all named 4 bromo 3 methyl 2 in, 1 bromo 2 methyl but 2 in, 1 bromo but 2 in, 3 bromo 2 methyl propene. Write structures of the following compounds: 2 chloro 3 methyl pentane. They gave it's basically there are 6 carbons in this compound because it's a methyl and a pentane. A pentane is the main chain where there are 5 carbons, and methyl at the third carbon there is a methyl group, and at the second carbon there is a chlorine group, chlorine attached, not a group but a chlorine atom, halogen is attached. And 1 chloro 4 cyclohexane, 4 ethyl cyclohexane. There is one ethyl group where the C2H5 is the ethyl group, and cyclohexane is basically a cyclic hexane group, which is C6H12, and from this C6H12 the formula will be C6H10, C2H5 and Cl. Both of these are attached at chlorine at the first position and ethyl at the fourth position. 4 tertiary butyl, 3 iodoheptane. It seems to be a heptane group, and butyl is the function an attached group to the main heptane group but not in the main chain. And this tertiary butyl is attached at the fourth position, and there is an iodine group attached at the third position. 1,4 dibromo butene. Butene, it's a alkene. There's a double bond at the second position, and there are 2 bromine atoms attached at the first and the fourth positions. And bromo for secondary, butyl 2 methyl benzene. The main group seems to be the benzene group. The benzene is the main group, and there is a butyl 2 methyl benzene. It's basically a toluene group, and at the second position there is a butyl group, and to this butyl there seems to be a bromine group attached at the secondary position or the fourth position. This is a secondary butyl. Okay, that was a little confusing, but fine. Now let's go to the third main topic, that is nature of the CX bond. Halogen atoms are more electronegative than carbon. Okay, therefore carbon halogen bond of alkyl is polarized. Halogen atoms are more electronegative than carbon. Carbon halogen bond of alkyl halide is polarized. The carbon atoms bear a partial positive, whereas the halogen atoms bear a partial negative charge. This is the representation here, a partial positive and a partial negative, where it is the partial is denoted by like this, partial plus and partial minus. As we go down the group in the periodic table, the size of halogen atom increases. This is normal because the atomic size, the number of shells increases. Fluorine atom is the smallest and iodine atom is the largest. Consequently, the carbon halogen bond length also increases from carbon fluoride to carbon iodide. Basically, since the size increases, the bond length also increase. Logical. Some typical bond lengths, bond enthalpies, and dipole moments are given in table 6.2, which we'll see, where the bond length of CH3F bond is the shortest of 139 and CH3I is the 214. Bond enthalpy of the C and F bond is the highest of 452 kilojoule per mole, but for CH3I it is the least, as there is the as bond length, generally bond length is inversely proportional to bond enthalpy. Higher the bond length, lesser the enthalpy. And dipole moment all are approximately the same, but we can say that the dipole moment of iodine is the least, followed by bromine and fluorine, with chlorine having the highest dipole moment. Alkyl halides are best prepared in best prepared from alcohols which are easily accessible. They are basically saying that alkyl halides, these are best prepared from alcohols. These alcohols are easily accessible. Methods now, one of the main topics of organic chemistry, that is methods of preparation of haloalkanes. The hydroxyl group of an alcohol is replaced by a halogen on reaction with concentrated halogen acids, phosphorus halides, or thionyl chlorides. Basically, the OH group, the hydroxyl, basically the OH group, we know that when the hydrocarbon gains an OH group, then it will become an alcohol. So this alcohol having an OH group, this OH group, if it is replaced by a halogen, then that is the preparation of halogen. I mean, not halogen, but haloalkanes. Haloalkanes are having halogens instead of alcohol, I mean OH groups. So when this OH group is completely replaced by a halogen atom, then we call it as preparation of haloalkane. This can be done with the reaction of these alcohols with concentrated halogen acids like HCl. HCl is the concentrated halogen acid, where hydrogen and chlorine, and phosphorus acids, I mean not phosphorus acids, but phosphorus halides. Reaction with phosphorus halides also provides the preparation of haloalkenes, and with thionyl chloride as well. SOCl2 is thionyl chloride. SOCl2, sulfur, oxygen, and chloride is the thionyl chloride. This is the most preferred method. It is preferred because in this reaction, alkyl halide is formed along with gases SO2 and HCl. Basically, after the reaction, in the reaction site, only the reactant will be present. Everything else, the other byproducts, will be evaporated. So this is most preferred, as we don't need any kind of filtration or separation or any headaches like that. We will directly get the haloalkane. The two gaseous products are escapable, hence the reaction gives pure alkyl halides. The reaction is of primary and secondary alcohols with HCl require the presence of zinc chloride. With tertiary alcohols, the reaction is conducted by simply shaking the alcohol with concentrated HCl at room temperature, constantly boiling with HBr 48% is used for preparing alkyl bromide. Good yields of Ri may be obtained by heating alcohols with sodium or potassium iodide in 95% orthophosphoric acid. The order of reactivity of alcohols with a given halo acid is tertiary, secondary to primary. Phosphorus tribromide and triiodide are usually generated in Psi2, producing the reaction mixture in C2 by reaction of red phosphorus with bromine and iodine respectively. There is many kinds of information given here. The first information is normally haloalkanes are prepared through alcohols. That is one of the first information, and it can be prepared when the alcohols react with concentrated halogenic acids or phosphoric acids or thionyl chloride. Thionyl chloride is best preferred because after this reaction with thionyl chloride, when alcohol reacts with thionyl chloride, the final products will be HCl and SO2, which are gaseous byproducts. So they will leave the reaction site, and normally the reactions in the reaction order, the important thing here is the order of reactivity of alcohols with a given aloe acid is tertiary secondary to primary. This is due to stability of intermediates. And when primary and secondary alcohols are taken to react with concentrated HCl, there needs to be a presence of a catalyst, that is zinc chloride. But with tertiary alcohols which are having high reactivity, the reaction is simply conducted by taking this two chemicals in a beaker and just slightly shaking them. The reaction will occur. That's how reactive it is. There is no need for heating here. And in case of production of iodides, basically haloiodides, haloiodides not haloiodides, iodoalkanes, when we need to produce iodoalkanes, basically the hydrocarbons containing iodine, this is produced by heating alcohols when we heat with sodium or potassium iodide, Ki or NaI, which is with in that is in presence of 95%, that may be a concentration term, orthophosphoric acid. In that case, if we do, we will get good yields of Ri, which is basically iodoalkanes. For preparing HBr, we need to take not for preparing HBr, but for alkyl bromides, for preparation of alkyl halides, we need to take alcohols. We need to boil with in presence of HBr 48%. This is used for preparation of alkyl bromide, and this is the order of reactivity of alcohols with a given halo acid is tertiary secondary to primary. Phosphorus tribromide and triiodide are usually generated in site or in situ, produced in the mixture by the reaction, and red phosphorus with bromine and iodine respectively. Okay, it seems they're talking about the last sentences here. They're talking about the byproducts which are produced in the reaction site. Phosphorus tribromide and triiodide are generated when there is a reaction of red phosphorus. When red phosphorus, it's a type of phosphorus which will react. If it will react with either bromine or iodine, then phosphorus tribromide and triiodide are produced. These are the reactions here. They gave the reaction equations. All are alcohols. ROH, which is the general formula of an alcohol. Alcohol reacts with HCl in presence of zinc chloride, it will give RCl plus water. And when ROH will react with sodium bromide and H2SO4, alcohol will react with sodium bromide and H2SO4 in presence of H2SO4, we will get bromoalkane or alkyl bromide, NaHSO4 and H2O. And in case of alcohol with px3 phosphorus trihalide, we will get 3 alkyl halides, phosphoric acid, and alcohol reacting with PCl5, phosphorus pentachloride. In this case, we will get RCl, POCl3, and HCl. When ROH alcohol reacts with red phosphorus and with halogen, then we will get same haloalkane or alkyl halide. Alcohol with reaction with thionyl chloride will get RCl, and SO2 and HCl in gas phases both will liberate. The preparation of alkyl chloride is carried out either by passing dry hydrogen chloride gas through a solution of alcohol or by heating a mixture of alcohol and concentrated aqueous halogen acid. This preparation of alkyl chloride, this can be carried out like one way. We pass like dry hydrogen chloride HCl gas. When we pass dry HCl gas over a solution of alcohol, this is the first way. The second way is take the solutions together, mix them and heat them together. But the above methods are not applicable for preparation of aryl halides because the carbon oxygen bond in phenols has a partial double bond character and it is difficult to break, being stronger than a single bond. Basically, in case of phenols, this is a phenol group, benzene with an OH group. These kind of methods are not possible because there is a partial double bond here. This double bond, due to resonance with the oxygen bond with the oxygen atoms, due to this resonance and partial double bond character, this oxygen bond, to break this bond we need more energy. So this kind of thing is not done in case of phenols for preparation of haloarenes. So from hydrocarbons, from alkanes by free radical halogenation, free radical chlorination, or basically that is preparation of haloalkenes from alcohols. From alcohols we saw these many methods. The next is through hydrocarbons. This is only preparation of haloalkenes that we are seeing right now. This is not the preparation of haloarenes. Haloarenes, the preparation we will see later. Hydrocarbons from alkanes by preparation of haloalkanes by through alkanes. This is by radical halogenation. Free radical chlorination or bromination of alkanes gives a complex mixture of isomeric mono and polyhaloalkanes, which is difficult to separate as pure compounds. Consequently, the yield of any single compound is low. Basically, when we do chlorination or bromination, that is when we take a hydrocarbon, when we take a hydrocarbon and a halogen together and expose it to sunlight, UV light, or altogether heat it, then a different mixture of compounds, like this is one kind of compound, this is one kind of compound, all will be produced. Many different kinds of mixtures of isomers of poly, mono, di, tri, halogens, everything will be produced. So it's not really ideal for when we are actually wanting a specific kind of compound. Now alkanes, that is a method. From what about alkyl halide preparation from alkenes? There is a double bond here. Addition of hydrogen halides, and alkene is converted to corresponding alkyl halide by reaction with hydrogen chloride, hydrogen bromide, or hydrogen iodide. When we take an alkene, when we take hydrogen halogen, hydrogen halide, which can be hydrogen chloride, hydrogen bromide, or hydrogen iodide, when we do a reaction with this, we will get the double bond is taken care of and we will get a haloalkane, propane. But in case of propane yields two products. However, only one predominates as per Markovnikov's rule. In case of propane, since it is unsymmetric. Here there is a double bond here, and in this case, according to Markovnikov's rule, this will be the major product, as according to the Markovnikov's rule, the negative part of a negative addition or a negative component, or which is substituted into the compound, which is substituted into the part which is having the least substituted carbon, which is added into the part which is added to the least substituted carbon, the carbon containing least number of hydrogens. That is why in this case, here where there are only one hydrogen and here there are two hydrogens, the iodine will be the negative part, the anionic part, which is attached to the carbon with least substitution, that is having least carbon, not carbon, I mean hydrogen. So here where it is only having one hydrogen, the iodine is attached here. So Markovnikov's rule, this is the major product. Now addition of, this is still from alkenes only, but in alkenes itself, addition of halogens in the laboratory, addition of bromine in carbon tetrachloride to an alkene, resulting in discharge of a reddish brown color of bromine constituents, an important method for detection of double bond in a molecule. The addition results the synthesis of vicinal dibromides, which are colorless. Let's read the statement again. We can prepare haloalkenes or alkyl halides through addition of halogens to alkene in the laboratory. Addition of, when we add bromine to carbon tetrachloride to an alkene, wait, the reactant here is not chloroform, I'm talking about carbon tetrachloride. It's better to see the reaction here. This is the alkene. I'll be back 1 minute. Okay, let's see this reaction again. When there is an alkene reacting with bromine in presence of carbon tetrachloride will give a vicinal dibromine or a dibromide, and addition of bromine in CCl4 to alkene resulting in discharge of a reddish brown color of bromine constitutes an important detection of double bond in a molecule. Basically, when we pass, how to know whether the compound here it is an alkene or an alkane? When alkenes have double bond, but we can't see individual molecules to see how many electron pairs they shared. That is why when we pass this bromine gas, which is brown color, it will react with an alkene to give a vicinal dibromide. This will change the color of the like reactants. Then we will know there is a double bond. That is the reason it is reacting. So it is not an alkane. If it was an alkane, there would have not been a reaction. But because it is an alkene, there is a reaction with bromine. That is why it's kind of a test. And identify all the possible mono. Okay, these are isomers in the given molecule. There are four types of hydrogen atoms. Replacement of these hydrogen atoms will give the following. They gave formed on free radical monochlorination. Free radical monochlorination, they gave specifically that it is a monochlorination. So there are butane, wait, 1, 2, 3, 4, 5, and in this cases it will be there are 4 chances, but there doesn't seem to be a chance of getting attached to these carbons. Okay, that is the case. There's a small topic here of halogen exchange. Alkyl iodides are often prepared by the reaction of alkyl chlorides, bromides with NaI in dry acetone. This reaction is known as Finkelstein reaction. Basically, when alkyl iodides, these alkyl iodides, basically preparation of Ri we are talking about. This is prepared through an halogen exchange where Rx, that can be chlorine or bromine, will react with NaI in presence of dry acetone. In presence of this, it will react to give a halogen exchange where this halogen is getting exchanged with Ni. Iodine group will get Ri plus NaX. NaCl or sodium chloride or sodium bromide thus formed is precipitated in dry acetone. It facilitates the forward reaction according to Lee-Chatelier's principle. The synthesis of alkyl fluorides is best accomplished by heating an allyl chloride, bromide in the presence of a metallic fluoride such as AgF, Hg2F2, silver fluoride, mercury fluoride, cobalt fluoride, tin fluoride. The reaction is termed as Schwartz exchange reaction, where it is a preparation of fluorines, where the alkyl bromide will react with a metal fluoride to give a displacement reaction, or a exchange reaction that will give alkyl fluoride and a metal bromide or a halide. With this, I'll be ending the stream. I'll continue this in the next video, hopefully. Then see you later.